the concentration of ions from pH of salts. This is the reverse of equilibrium, acid-base equilibrium 7, okay, Pencast 7, because in Pencast 7 we were trying to calculate the pH, but now we're going to calculate the concentration of ions, okay, so we're going the other way around now with this. Okay, so what is the molarity of ammonium nitrate solution with a pH of 4.80, all right, and the Kb is given to us, which is really a good idea. So then NH4 plus yet again is acidic salt. Okay, if it's an acid salt, then you need Ka. If you need Ka, then you have to do the side calculation over here with the Ka is equal to 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, which is 5.6 times 10 to the negative 10. Alright, so we have to do this in order to find the Ka value. Then we're going to go ahead and set up our equation once again. Since this is for a salt, I'm going to not worry about the nitrate because that is coming from a strong acid. I'm going to worry about my ammonium ion plus water, and as a result of this, the water is going to pick up a proton to give H3O plus, and then the ammonia is going to remain as NH3. So then our initial concentrations that we had for the ammonium ion, okay, and all that good stuff is actually X, okay, for this, because why? We don't have the ammonium ion, we have the pH, okay, so which means that we need to find hydronium ion concentration. So this is step number 1 here. Step number 2, hydronium ion concentration. So antilog of 4.8, which is equal to 1.6 times 10 to the negative 5 molar. So you have 2 calculations to do on the side before you can actually do the problem. All right, so then initial concentration 0 and 0. So the change then is that because we have an acidic salt, you're going to form 1.6 times 10 to the negative 5 molar of the hydronium ion and 1.6 times 10 to the negative 5 of the ammonia. Okay, and then meanwhile you're also subtracting the ammonium ion from here, so 1.6 times 10 to the negative 5. So when your pH is given to you, you have to work in the reverse manner, which means you have to work from product side, not from the starting material side. And then at equilibrium you have concentration of X minus 1.6 times 10 to the negative 5, and then of course the 1.6 times 10 to the negative 5 and 1.6 times 10 to the negative 5. So those are your concentrations. So now we're going to set up our Ka, because this is acidic salt. Ka is 5.8 times 10 to the negative 10, and this is equal to 1.6 times 10 to the negative 5. I'm just going to go ahead and square that because we have 2 of those. And X minus 1.6 times 10 to the negative 5. Now in this case you cannot ignore X because that's what we are calculating. All right, X is the concentration of the ammonium ion, so you can't ignore X. Okay, in this case that would have been this anyway. So then our X turns out to be 0.46 molar. Okay, so go ahead and do the calculation on your own and see if you get the same answer. All right, so that is how you would calculate the molarity. Now let's do another one of those and see if we have gelled this, okay, because there's always something else. So what is the molarity of sodium acetate solution of a pH 9.10? The Ka of acetic acid is given to us, 1.8 times 10 to the negative 5. Now CH3COO minus is weak base, so we need Kb. The other thing also, of course, is that since this is going to be a weak base, we are going to need hydroxide ion concentration, not hydronium ion concentration. So need hydroxide ion concentration, okay, from the pH value. So we have our side calculations to do for us already, And so first of all, let's go ahead and calculate the Kb, which is 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, and that is equal to 5.6 times 10 to the negative 10. Our second calculation that we have to do is of calculating the POH, okay, because we have pH here given to us. So POH is 14 minus 9.10, which is equal to 4.9, and so then take antilog of 4.9, and this should give you 1.26 times 10 to the negative 5, and this is going to be your hydroxide ion concentration. Okay, so now we can set up our problem. And so CH3COO minus is where I'm going to start, the acetate ion plus water to give me acetic acid, and the hydronium ion, because that is what is formed, because this is a basic salt, so you end up forming, I'm sorry, very sorry, going to form hydroxide ion, okay, because this is a basic salt, so you end up forming hydroxide ions. Alright, so then let's go ahead and plug in our values. For the initial concentration, this is X, that's what we're trying to figure out. Everything else is 0 and 0, and then for the change in the concentration, that is what you just calculated here. So the change here is for acetic acid, which is going to be plus 1.26 times 10 to the negative 5, and then for the hydroxide also plus 1.26 times 10 to the negative 5. Okay, so and then here for the acetate, that's going to decrease, so 1.26 times 10 to the negative 5. So then at equilibrium you have X minus 1.26 times 10 to the negative 5. This is 1.26 10 to the negative 5 and 1.26 times 10 to the negative 5. So then we're going to set up our Kv, not Ka, because we're working with a weak base. So our Kb is equal to 5.6 times 10 to the negative 10, and this is equal to products over reactants, so 1.26 times 10 to the negative 5, and I'll just take the square of that, divided by X minus 1.26 times 10 to the negative 5. Alright, again you cannot ignore X, so now X is equal to 0.29 molar. Okay, so on this page you have two calculations, one for an acidic salt and one for a basic salt. Alright, for acidic salts the calculations are slightly different over here, okay, and for basic salts you start with slightly different things here. So please make sure that you're working with the right kind of Kas and Kbs and hydronium ion and hydroxide ions.